Another main topic of this section is asymptotes. So these are boundaries in the function. They are represented with a dashed line. So if you see here, we have a vertical boundary. That's a vertical asymptote. We have a horizontal asymptote. That's a horizontal line. It's a boundary in the function. So these really warp the function. If you see here, these lines will approach, or I should say these graphs will approach these boundary lines. So it really breaks up the function. The vertical line x is equal to a is a vertical asymptote if y approaches positive or negative infinity as x approaches a from the right or the left. So that's just kind of talking about the generic form of that vertical line. So kind of as an example, if our function is like 1 over x, so I want to try plugging in some numbers. If you just take 1 divided by 0.1, then you'll get 10. Then if you do 1 divided by 0.01, you get 100. And then 1 divided by 0.001, you get 1,000. So this is getting bigger. And it will go all the way to infinity. It will just keep getting bigger and bigger and bigger. So what this represents is approaching 0 from the right, which the notation for that is x approaches 0 plus, or as you approach 0 from the right. So these numbers that I'm picking, those are getting closer and closer to 0, and they're all positive. The other one is if we get closer and closer to 0, but they're negative. So if you take 1 and divide it by 0.1, or sorry, 1 divided by negative 0.1, then you get negative 10, and then divide it by negative 0.01, then you get negative 100, and then you also get negative 1,000. So this is going to negative infinity. And this would be as you approach 0 from the left. So these numbers get closer and closer to 0 from both directions. And functions are defined, or I should say functions are undefined at vertical asymptotes, because right at that 0, y is equal to 1 over 0, it would be undefined there. But if you're just a little bit further away, it's really like these extremes of going to infinity or negative infinity. So our process actually to find the vertical asymptotes is to set the denominator equal to 0. With horizontal asymptotes, it's a little bit different. These are the horizontal boundaries in the function, and if you want to give it a generic form, it would be y is equal to b. They're really the end behavior. So it's like as you go super far to the right, or you could say x goes to positive infinity, or as you go all the way to the left, or you could say x goes to negative infinity. So because of this, we are only concerned with the leading terms, or the highest degree, of the numerator and the denominator, because these terms dominate. The other terms are important, but these ones take over, especially as you go to the far right and to the far left. So if we look at these leading terms, for the first one here, this is 3x over 2x squared. If I reduce that, the x will cancel out, and you'll have 3 over 2x. And then if you go to the extreme, so as you go to the far right, this is going to be, if you plug in infinity here, 2 times infinity is still a super large number, it's still infinity. So this would be 3 over a large number. And just like we showed before, well, we actually showed divided by a small number. So how about we take 3 divided by a super big number like a million, and we get 3e So I did 3 divided by 1,000,000, and I got 3e negative 6. So that's a super small number. So that effectively is actually 0 here. So the horizontal asymptote would be y is equal to 0. Let's look at this case here where we have a 3x squared and a 2x. So on this one my higher term was on the bottom. Here my higher term is on top. If I reduce this, this is going to be 3x over 2. And then if I plug in infinity, it's going to be a large number over 2, which just equals infinity. So y is going to be equal to infinity, or really it's going to be no horizontal asymptote, because if this just keeps going and going, there's no boundary. If there's no boundary, then it's not an asymptote. So there's no horizontal asymptote, and this is because there's no boundary. And then the last case is if we have the same power. So the first one was the higher degree was on the bottom. The second one was the higher degree was on top. Here the degrees are the same. So if you take those leading terms and then you reduce them, you get 3 over 2. So if you plug in x going to infinity, there is no x, so this is just still 3 over 2. So y would be equal to 3 over 2. So that's just kind of explaining where these cases are coming from. You don't need to do all this work every single time. You just need to know these 3 cases, because this will work for all of them. So if the numerator has a lower degree than the denominator, then the horizontal asymptote is y is equal to 0. If the numerator has a higher degree than the denominator, then there is no horizontal asymptote. And if they have the same degree, then it's the ratio of leading coefficients. So it's like on this one, we had a fraction of 3 over 2. That is our asymptote there. So those are our cases. Let's look at number 5. So it wants us to find all horizontal and vertical asymptotes. So to get the vertical asymptote, I want to set the denominator equal to 0. So I have 4x squared plus 1 is equal to 0. If I subtract 1, I have 4x is equal to, 4x squared is equal to negative 1. And divide both sides by 4, and then take the square root. And we get square root of a negative number. Now we are not considering imaginary numbers in this. So this is imaginary. So what that actually means, because we're getting an imaginary number, it means that there's no vertical asymptote. So normally we'll just get a number here, but if you get an imaginary number, it means that there's no vertical asymptote. For the horizontal asymptote, I want to compare the degree. So the denominator has a higher degree. Because its degree is 2, and the numerator has a degree of 1. Therefore, y is equal to 0 will be our horizontal asymptote. And just as a note, you don't need to put this, but this is a horizontal line. This is not a point, this is a boundary line.